Hey, welcome. We're going to just discuss quickly some vocab words and some concepts that involve testing a material for its tensile strength. So this is just an introduction to the concept of testing a material for tensile strength. Now, I found this video here real quick. I'm going to go ahead and play. I don't know if you can hear it. I don't think the audio is recording, but what we've got here is a sample material. I've got some pictures prepped too. These are different examples of materials cut down to what we call the dog bone shape. So these are different materials and some different shapes that they use. Right now in the video you're seeing these cylindrical pieces with the threaded ends. They actually were threaded in. Okay, and then the machine is pulling. And as you continue to increase force, the idea is that we're going to load this material until it breaks. Okay. So what's happening right now is the material is actually starting to stretch, and as it stretches, it gets thinner because there's only so much material, and if it's going to cover more distance, right, it can't maintain the same width. It's got to spread out a little bit to be further apart. But it does, in fact, stretch. They tell us here in the title that this is a stainless steel sample, and eventually it's going to break. Right there. That process where it is starting to deform, okay, and narrow is actually called necking. All right, so that gives you a visual aid of what's happening real quick, and then let's just kind of start to understand some of the vocab here. So I'm going to switch over to my dot cam. All right, here we go. Okay, so let's think about this. You've got a material, right, that you want to test, and the idea is you've got it at rest. It's got no load on it, so it's some given length, right? And you're going to apply a force. All right, and as you apply that force, in theory, right, we may be able to actually stretch the material out, even a material that you thought we couldn't stretch out, like steel. Okay, so you saw in the video that it did have the ability to stretch a little before it broke. Okay, the amount, that distance that it stretched, is a word we call elongation. Okay, basically it's a fancy word for how much it stretched. So I want you to get the idea that we can take a material that wasn't under load with some distance, some length, and as we put it under tension, as we load it up, that it's going to get longer. So this distance right here, this amount in my little graphic, represents how much longer it is, or how much elongation happened, how much it stretched. Okay, let's think about what would happen if you started with a longer piece of the same material. Okay, kept everything the same. We're going to apply the same amount of force. The force is the same, the material's the same, etc. Okay, so what happens is we've just got more length, right? And is it going to stretch more or less? Well, what we would say is that, if I take a small sample and pull on it, there's just not that much material to even stretch out. So, if let's say we were expecting to get 10% of stretch, well, 10% of that little number is not going to be that big. But if I can get another unit and I can get a little bit of stretch out of that piece, and add another section and get a little bit of stretch out of that, another section that's going to stretch a little bit, that the overall distance of stretch might be longer simply because I had a longer sample. Does that make sense? So elongation, how much it stretches, we want you to understand, is going to be based on how long the sample is. Okay, amongst other things too, but that's one of the variables. All right, so if I take this material and I recreate the sample, the load, if you were to slice it and kind of look at the size of the sample, keep that the same, call that the cross-sectional area, keep all the variables the same except for the length of the sample, we would expect that the longer sample would actually have more stretch, that we'd kind of get that same amount per unit. So if that was 1 unit of length, that for that unit here we'd get this next original unit we'd get this, and this next original we'd get that. So kind of together, combine those three, we've got all this extra, right? So it looks like it stretched 3 times more, but it's just because it was 3 times as long. Okay, so not too profound of an idea, but it is important. So that is explaining what elongation is and setting the stage for us to understand what strain is. Okay, so elongation, the amount of stretch it is, since it's based on the length and not just on the material alone, we wanted a way to kind of normalize that, okay, so that we can understand really just the material itself and be taking and removing the idea of the variable of what size sample we used. So given the constants of material, the sample diameter, okay, the force, the amount of stretch will vary based on length. That's what we just said. Okay, we'd like to normalize this. We want the basically what we'd call the unit rate of stretch. So per unit length. How much stretching do we get per unit? That is something we're going to call strain. Okay, so strain is not just straight up the elongation, the amount of stretch, but it's the amount of stretch per length, per unit length. Okay, so strain is this E symbol. Elongation I didn't point out in the other slide, but is this symbol. Okay. All right, so strain is really just the quotient of how much stretch we got over the original length. All right, and then if you divide this, you're really in essence reducing this down to a denominator of 1. So we're trying to get down to a unit rate, kind of a how much stretch per unit of length. Does that make sense? All right, you think of unit rates in math class. We're really trying to understand how much per unit, per 1 unit. So in this case, it happens to be the amount of stretch per length. Okay, so that is what we call strain. So elongation is going to get translated into strain. Hit the pause video. Okay, so hopefully that makes sense. That the amount of stretch could be based on how long it is, and so we're trying to just remove that idea. Okay. The next thing I'm going to talk about is the difference between load and stress. So another variable other than length would be kind of that cross-sectional area. If you take one of those samples and were to slice it and look at the end, okay, are all samples going to be the exact same size? Well, and even in the picture I had up, you can see that the diameter of this sample is larger than the diameter here, and these pieces are not the same. These are actually close to being the same size, these three, but this one is clearly bigger. Okay, so that makes sense. Let's flip back over to the hover cam. Okay, so the key question you should ask is, what if the cross-sectional areas were different? Which one would experience more stress? Given, I guess I should point out, given that we are going to put the same exact load, these are going to be a constant now. So imagine that we try to keep everything consistent. The length of the samples, the amount of load, the materials, all that, everything else is going to be the same. The only difference is going to be that cross-sectional area. So in this case, if they were around just a larger diameter, what one's going to experience more stress? Well, if you think about it a little bit, there's less material here. Getting the camera's kind of getting overexposed somehow. There's less material that has to hold up to all that stress, all that tension with just less atoms, less molecules here in the sample, right? Here, there's a lot more mass to help share the load. So it would make sense that the smaller piece is going to experience more stress. Each, kind of at the atomic level, each atom in here making up this material, it's got to experience more stress. Okay. The idea of both of these things that we've talked about, elongation translating into strain, and now load, trying to understand the load as a stress, is that we really want to remove variables that have to do with the sample size. We really just want to understand the material property. So we're trying to get information that is now based on the material, not so much based on the sample size. So just like translating elongation and strain, here we're going to try to translate load into stress. Okay, so we would expect that this would start stretching and necking faster than this one under the same load, or trying to bring them up to the same load, right? Okay, so stress instead of load is going to be the amount of load we get per unit of cross-sectional area. So if you can come in and measure the area here of a sample size, okay? So if this area, okay, I'll just do sub 2, of sample 2 compared to this area of sample 1, let's say the area here was 5 times larger, okay? Which you may think that doesn't look 5 times larger, but really I can almost get 4 of those circles fit inside that circle. Maybe not, maybe it'd be 4 times, but, and then there's some extra space in there, but this very well could be graphically, you know, something that looks like it's 4 to 5 times larger. Okay, so there's a lot more mass to carry the load, so we're going to divide the load by the surface area of that section view. Okay, so that's what we're calling the cross-sectional area if you were to slice it and look at that area. So dividing by that, that is going to get us down to kind of the unit, kind of the load per unit of surface area, if that makes sense, and we call that stress. All right, stress, the symbol is a lowercase sigma. Okay, looks like that. And the load is just a force. So it's the force divided by that cross-sectional area, and that is stress. So we have 2 variables now. We've kind of 4, right? We started with elongation and strain, but really these are very similar, right? Elongation is the amount of stretch. Strain is the amount of stretch per unit length. And then we've got load is how much force we put the sample under. And stress is how much force per unit of area. Okay, so these 2 are very similar, right? Both kind of dealing with the force or stress. These 2 are very similar, both dealing with how much the sample stretched. Okay, these are similar in that they don't take into account the sample size. These do. Okay, these have been translated to where we've divided by the overall length. We've divided by the amount of area we have cross-sectionally, so that these are helping us understand per unit. So when we want to graph data and start looking at understanding the material, especially to now compare one material to the next, it is stress and strain that we're going to want to look at graphically, since these have helped remove the variables of length and kind of size, length and cross-sectional area size of samples, so we can really just compare the properties of tensile strength for that material. Okay, hopefully that all makes sense, and we'll continue on with the next lesson.